So I'm Richard Jones, and we're going to have a break from PowerPoint. I'm the leader of Work Package 2, Surfaces and Interfaces. So what we're going to do is I'm just going to say a few words about what the problem is, and then I'm going to ask some of the researchers some key questions about that. So if you paint something, if you paint a surface, what you see is the top, but what matters is the bottom, particularly if we're talking about stopping corrosion. So what our project is about is what's going on at that, right next to the substrate that you've painted. What's the nature of that paint film close to that interface? Now, in the trade, there's this term called the interface, which is a kind of woolly term that says we don't really know what's actually happening at that interface. It's probably different from the rest of the film, but how's it different? And our project really is trying to find out what the differences are. Why is that region of the paint film, the region of the organic coating next to the substrate, why is that different from the bulk? So just to kind of tell you a bit of an insight about how we're addressing that question, I'm going to ask some colleagues to come up to the front. I've got Mark, who's here, from our colleague from AkzoNobel, Melody, Suzanne, Stephanie, and Andy. I hope you can appear. So I'm going to start with Mark. So Mark, you're a collaborator from Akzo, and it's been great to work with Akzo. It's been people were competing with how long that they've worked with Akzo with. Actually, my first ever academic job, I arrived in Britain in 1989, and pretty much the first thing I did was go to Gateshead and to go to Felling, talk to International, as it was then, about the nature of polymer surfaces. Then I had a long engagement with ICI. But so Mark, you've worked in different bits of the paint industry. Tell us a bit about how your experience with different kinds of paints and different kinds of coatings, and why the interface matters and what's different between them.
Thank you, Richard. Yeah, my guilty secret, I guess, is that it's only very recently that I've been involved in anti-corrosive coatings. My past, the majority of my time in my career, has been working with what AkzoNobel terms decorative coatings. And these are pretty much the paints and coatings that you would buy from stores like B&Q or Wickes. So, sort of you see them around the walls here. And obviously they offer a very different performance proposition from what you would expect with an anti-corrosive coating. And there's a lot of very smart people in the room, so I won't patronize you by emphasizing what those differences exactly are. But suffice to say, there's a reason that we don't recommend painting boats with Dulux vinyl matte, despite that it's a really good product for your wall. There are, however, some similarities between the areas, and I guess probably the two I'd like to focus on are the drivers where we're looking at new products. One of them is around sustainability and reducing the embodied carbon in our coatings, and this applies really to everything that AkzoNobel sells. In the deco area, most paints that you buy nowadays are water-based. That wasn't always the case. It's a lot harder to make that sort of transition with anti-corrosive coatings, in part because of the chemistry involved, and in part because of the environments where they're applied. If you go to a boatyard in South Korea in the middle of winter, you'll find people applying coatings onto boats at 5 degrees at relatively high humidity. And these are simply not going to dry before it drops below zero overnight. You get issues with freezing, and that's a huge problem if your carrier solvent is water. So instead, the way that anti-corrosive coatings adapt is by moving to increasingly high solid systems. And that's not without its challenges. Obviously, as you pull solvent out of a system, it becomes more viscous. And these things have got to be capable of being spray applied, so we're adding in other ingredients, things like reactive diluents, in order to allow these systems to be at a viscosity where we can still apply them sensibly onto substrates. And that fundamentally changes how these systems cross-link, how the films form. And hand in hand with that, as new products are introduced, there's a requirement for increased performance. And again, this is true both of decorative paint and for anti-corrosive systems. And a big part of that is knowing how your current coatings fail, so that you can address this and have ways of developing newer technology for the products in years to come. And that's really the two areas where Work Package 2 can deliver really important results for AkzoNobel. So we're interested in fundamentally what happens to polymers. We heard, I think yesterday, about the importance of phase separation in polymers, Andy, and from you, Richard, about the importance of the interphase in these systems. And those are both key to understanding how a system is going to perform. And obviously, as we make these changes to keep coatings current with what is needed, these things will change as well. And it's only by knowing in really very high detail what is going on at these key surfaces that we can hope to develop products for tomorrow. So thank you very much, Richard.
Thanks, Mark. So you talked about, you put a coating on, it cures. We're in the Korean shipyard, the stuff cures. There's chemistry going on, speaks a physicist. Something, all kinds of stuff's happening in there. I'd say, Suzanne, you're the one who knows what's that why is the chemistry? Why might that be different at the interface? And how can you find out what's going on?
When you change the conditions for curing or anything, when you apply a paint, we have precursors. Obviously, they don't appear ordinarily. We don't have a fully cross-linked network to begin with. And those precursors are going to be interacting with whatever surface you apply the paint to and with your pigment surfaces. And we think that the chemical gradient that forms there, which will happen because we would expect that one of those precursors will interact more with that surface, or will have a higher mobility, and again that would depend on the cure temperature. So we'd expect we'd have a chemical gradient there. It's going to be very, very, very small in depth, so we're talking kind of sub-nanoscale. But in terms of corrosion resistance and performance, you're going to expect to have, if you have a large chemical difference at that interface, you may have leaching, you may have species that are more susceptible to oxidation. Essentially, the chemical structure of that interface is going to determine your adhesion and disbondment, how water transport at that interface. So it's really important, but it's also extremely difficult to study. So we're talking about a very, very small amount of material buried underneath a large amount of essentially bulk material. So what we've been doing is trying to look at ways to section that kind of interface and look at that directly. So in my case, using AFMIR spectroscopy. So that's a scanning probe microscopy coupled with infrared spectroscopy.
So you've got a really smart microscope that can look at chemical differences near the interface, and it's really just a few nanometers, isn't it? It's really small. But so we've got chemistry might be different, but the physics could be different too. And we think maybe near the interface it might be harder, it might be softer because it's kind of glued down to that interface. The molecules can't move around as much. Maybe they can move around more. So that's this question of how can we find out what's going on with those molecules? That's something that Stephanie's been looking at. So Stephanie, come and tell us why that is such a fiendishly difficult problem to look at experimentally.
All right. So as Richard already said, we're interested in the bottom. And when we're talking about my work, which is about mobility and diffusion, these are things that happen in time. So I can't cut it open and look at it in the way Suzanne does because she's interested in a static thing at the surface. I want to know how things are moving and changing at that surface. So I have to look through the film in order to understand what's happening in it. So the first problem is that in order to look through the film, I need to make it really, really thin. So I've got a sample prep problem, and I need to take these coatings that are sort of normally microns and bring it down to nanometers. And then I need a way of looking through the film. So that means I need to employ some sort of radiation technique, be that light, be that X-rays, be that neutrons, in order to look through the film while I'm changing something. But these sort of radiation techniques they're not a direct measurement of anything we want to know. They're not going to actually tell me what diffusion or mobility is happening. They're going to measure something, and then I have to fit the data, which means I need to create an answer that I think is happening, and then check whether that answer matches what I've measured. So in a way, I almost need to know the answer to get the answer. And we sort of wrap all of these problems together. And if we do this correctly, we should be able to develop a model that we know and understand, have a material that we've made in a really, really thin geometry, and looked through it while we change how much water is in the film or the temperature and how things are moving. And then ideally, we can wrap that together and understand what's happening at this interface that we can't actually see directly, because if we cut it open, we'd probably change the answer.
Right, thanks. So Stephanie, you're already given away a little bit of our secret. So these are really sophisticated techniques we're using. So Suzanne's techniques allows us to do chemical analysis really on the nanoscale. Techniques that Stephanie's using are sensitive really to nanometers. And our little secret is that we don't actually go and take a plate off a ship that's been painted in a Korean shipyard. We need to make samples that are representative of the physics and chemistry that we think is going on in real coating systems, but we need to make these samples in a very controlled way. And that's not been totally straightforward. And Melody, as our chemist, has been able to, will tell us quite what she's done to get us these samples, particularly things about cross-linking, getting cross-link samples in really thin films where we can access that buried interface.
So just to paint a picture of the challenges that I face, pun intended, is that with the hardener that we're using for our systems, it's extremely volatile. And so if I have a proportion of what I expect to be in this mixture, some of it is going to evaporate. And being able to determine how much of that evaporates hasn't been the easiest road. Then also making these formulations, I've got two sort of processes that I'm competing with. I have the fact that there's vitrification that's happening, and that basically describes the polymer chains when they're less mobile. As the 3D network is forming, as this polymer network is being made, the polymer chains are being held back by the cross-links that are connecting them together. But then also, as you're getting this 3D network, it's becoming a lot more insoluble. And so what I have to do is kind of play around with the proportions of the hardener and the epoxy that I'm putting together. And with that, also the evaporation of the hardener. So yeah, it's not an easy road, but we're getting there.
No, you've done a great job on that. And just to, so what we're interested in, we're interested in what the nature of this interface is as it's made, but then we want to worry about, how does water get through? How do ions get through? How do the things that actually cause the corrosion, how do things get to that interface? So we've got to think about transport. We've got to think about how things get through. We need to think about, how should we think of this? Is this like a little sponge where we've got little holes in and the water's jumping from hole to hole to hole? That's something that Andy's been thinking about. So tell us a bit. Do we really believe in free volume?
Whether or not we do, Richard, it's actually a remarkably good analogy for trying to understand what's going on in these systems. And at the moment, we're using it to sort of qualify the and compare systems, which I think is a very useful tool, whether or not it's strictly physically correct or not. But what we're interested in is looking at how the polymer dynamics, and these are not just rigid ceramic type materials with holes in them. These are dynamic systems, and their dynamic state depends on temperature and solvent, and so water in this case. And so understanding what's going on at the surface, in the bulk, and at the buried interface, where we might expect to see different dynamics, is really important. And we know that that will affect the uptake and movement of ions, because we know that in terms of corrosion, we need these hydration shells around particular ions to impart mobility to them. So, having a certain free volume, or limiting that free volume by tailoring the networks that we make and the chemistry that we use, is really important to be able to control the free volume inside our system, and then understanding how connected these free volumes are, so the tortuosity of our internal polymer network. And again, in future systems, trying to understand when we try to move to newer systems, how does the change in the morphologies that we get, how does that affect the dynamics and movement of water and again ions again? Do we make much worse systems, and can we try and improve? So by tailoring the nanostructure inside, or the molecular and nanostructure, this sort of very fine length scale that is really hard to measure, even with AFM, we can use our scattering techniques in Sheffield and other labs around the UK and Europe that we use to understand what is the nanostructure that controls the mobility and the freedom for our coating to resist corrosion at these very precious metal and organic interfaces.
Great. So we have some kind of physical pictures, and we argue about these physical pictures. This is part of a bigger project, of course, so we have to. So we're not operating in isolation. We work with our colleagues who are doing sophisticated theory and modelling about these, so we can really connect that to theory. And also, as I say, we're looking at quite model systems, but we know we need to connect that more to the actual paint systems that actually do go on ships and aeroplanes. Many of those are filled. They have more. It's not actually just a quote. When we talk about the interface, we're not just talking about the paint on the substrate. There's often fillers there too. So I hope that's given a bit of a sketch. I don't know if you want to add anything from Axo's perspective, having about the problems that we've got so far and how you see this sitting into the broader picture, Mark.
Nothing major that I can really contribute at this point, I'm afraid, other than to say that the problems are very real and that they are very difficult. And it's great that we've got some of the brightest minds working on this. And I'm looking very much to what comes from this work package. Thank you.
Great. So I hope that's given you a bit of a picture of how we think about this problem, how we've broken it up, how we're trying to address what I think are both really actually pretty interesting fundamental scientific questions, as well as questions that I hope have got a really significant relevance to Axo's business. So with that, thanks very much.